Assalamu alaikum and welcome to lecture number 24. In this lecture we are going to discuss some more numerical problems on Fourier series. We will talk about the second method of finding the Fourier series coefficients, that are a method called finding Fourier series by inspection method. Okay, in the previous lecture we have done this numerical problem, and from this numerical problem it is very clear that the signal we obtain is this one, and it can easily be noticed that there is no term that involves t, right? So you can say that this is a basically it is a frequency domain signal. Now the independent variable is frequency, not the time. So we have this example and you can see different graphs, and all of these are independent of time. So let's consider one more example on finding the Fourier series coefficients. So the given signal is x of t, which is equal to sine of omega naught t, right? To find the solution of this, first we use the Euler formula to convert the sine or sinusoidal signal into exponential signal, right? So the equation to find the Fourier series coefficient is ak 1 over t integration over period. You understand that we multiplied the signal by e power minus j k omega naught t, and then we integrate it over one period, and the resulting value is scaled by a factor of 1 by t, where t is the time period of this signal, right? So by putting the value here, we find that ak equals to this, right? So I just replace the values from the this Euler identity. So by simplification we get this value. I hope you understand how I did it, because both of the two signals are the complex exponential, so they are multiplied. So multiplication means we can simply add their powers. So adding the power will result into this, and for the second term we have this, right? And we are integrating it from 0 up to t. You understand, we can take any value of the period. We can take from minus t by 2 up to t by 2, or we can take from 0 to t or t to 2t and so on. But the important thing is that you integrate it over one period. So by looking at this equation, basically this is equals to, this value is equal to 0 for all values of k. And why this is equal to 0? Because if I expand it, then I have the, okay, let me expand it. So just if I expand this, so I can just write e power minus j k minus 1, right, times omega naught t. So if I use the relationship, so it can be easily written as cos of minus k minus 1, right, into t plus j sine of minus k minus 1 into t, right? So the complex exponential periodic signal will result into this, right? So if we look at this one, we can see that we have two sinusoidal signal cosine waveform that is real, and the this part which is imaginary is sine waveform. So clearly you understand, if I plot the sine wave, it will be something like this, okay, just, and the cosine wave something like uh, right, roughly. Okay, so this is one period. Okay, from here to here we have one period. Okay, so if I use the, this is 0, okay, and this is t. So you understand, because we are just integrating. So if I integrate, this is the imaginary part. So if I integrate, I hope you understand, this will result into integration of this will result into 0. And why 0? Because it has the similar values of negative and positive, right? So just adding them will result into integration. It's just the addition or summation for the continuous values. So if I integrate it, so hope you understand, it will result into 0. Similarly, for the cosine case, we have as many positive values, as many negative, and they all have same amplitudes. So summation of this or integration of this will also result into 0. So that means if I sum it, right, for all values of k, it will result into 0. But if for the value of the k, where k equals to 1 in this case, right, so if this thing becomes 0, so this will only become 0 when k equals to 1. So 1 minus 1 will be 0, and then we get some value. So if k equals to 0, right, so in short we can say this will be equal to 0 when k is not equal to 0, when k is not equal to 1 for all values, right, whether k is 0 or 1 or k is 100, 200 or minus 100, minus 200. Because if k is not equal to 1, in that case all these values, they will result into 0. And why they will result into 0? Because if you expand this one, so this is basically two sinusoidal signals, right? One cosine waveform is the real part, and the sine waveform, which is the imaginary part, right? So either sine or cosine, both, if integrated over one period, they will result into 0. So that means this waveform, this signal will be exponential for all values of k except k equals to 1. When k equals to 1, this will become 0, and e power 0 will result into 1, and we have the value, right? So when k equals to 1, again if I put 1 here, so 1 plus 1 2, I have a complex exponential signal, and summing it over one period, it will result into 0. Okay, so for example, if I put a k of, for example, 1, so in this case this will be 0, right? So I will get 1 by t, right, and 1 over 2 e power j dt, right? And again we have minus here, so if I put minus here, okay, I am just talking about the k equals to 1. When k equals to 1, so this exponential will have value something like 1 by 2j and e power minus j, and k is 1, so 1 plus 1, right? 1 plus 1 will be 2. So again we have a complex exponential signal, and we are integrating it over one period. So that means for k equals to 1, this term will be equal to 0, and you understand why this will be equal to 0, and this will result into this thing. Okay, so again, if I put k equals to minus 1, in that case this term will have value of minus 1, and minus 1 minus 2, So again, integrating it over one period, this term will result into 0. So for a equals to that is because ak, this is right. So if I replace k with -1, so it will be -1. So I put -1 here. So hope you understand, it will be 0. Whereas this term will have value that is equal to this one, right? So you understand, for all k values it will be 0 except for the k when k equals to 1 or when k equals to -1, right? So this is the output for the sinusoidal signal. So output here is basically what? It is the Fourier series coefficients, right? So this is your frequency axis. So if we look at the Fourier, signal, which was original signal, sine omega naught t. So for the case of sine omega naught t, we get the Fourier series coefficients, which are k equals to 1. So this is basically omega naught, right? Because the coefficients are at k omega naught, right? The coefficients are at k omega naught. So when k equals to 1, okay, when k equals to 1, we have this value. So this is how much? This is 1 over 2j. So this is 1 over 2j. And when k equals to -1, so that will be the point where we have minus omega naught. So at minus omega naught, we have minus 1 by 2j. Okay, you can also make them plus, because if you multiply the j with this term, right, if I multiply j with this term, I'll get a1 equals, multiply and divide, right? So a1 equals to 1 over 2j, right, and multiply by j and divide by j. So j multiplied by j is j square equals to -1. So this can be also be written as minus j by 2, and similarly this one can be written as which is a minus, and this is equal to j over 2. So in that case we have something like this. So this is your axis. For at omega naught we have j by 2, and at minus omega naught we have this omega naught, and this is minus omega naught, and this is your omega or the frequency axis, right? So here it is j over 2. So both are same, right? I hope you understand. So we did these examples using the Fourier analysis equation, right? So we have one more method that is called the finding the Fourier series coefficients using inspection method, right? So we can also do it using the inspection method, and that's quite straightforward. Here, instead of using the Fourier series analysis equation, which is this one, right, we use the synthesis equation, right? So to use this synthesis equation, we first express similar to the one we did for the analysis method based calculation. So we first express sine omega naught t in terms of using the Euler formula, right? So that's using Euler formula. So if I expand this equation and equate the coefficient, right? So because you can easily see that it has only the frequency first harmonics, that is we have the non-zero values at omega naught and minus omega naught, right? So I just say, okay, x of t, which is equal to sine omega naught t, right? So this is, if I open this summation, so all are 0, right? You understand? So I just say okay, or maybe you can also, if you want to do it in generalized way, you can say okay, this is equal to blah blah blah, and then you say plus, they say for example k equals to -2. So when you replace k here with -2, so it will be something e power, you understand, k is -2, so minus j, so I will write minus j, minus in fact 2j, right? Okay, I write here omega naught t, then plus a of -1, and I write minus j omega naught t, and then say here plus, when this is k equals to 0, so anything multiplied by 0 equals to 0, so e power 0 equals to 1. So I will just say okay, this is the DC value, which you know is the average value of the signal, and you understand this is your sinusoidal signal. So can you tell me what will be the average value of this signal, right? So that's straightforward. The average value of this will be 0. Okay, because you take average over one period, so if you sum the positive values and these negative values, this is your period. Okay, so this will result into 0. You understand, right? So this is something like this. You start with this one up to this one. This is one cycle, right? One period. So if you sum these values, because to take average you sum them and divide them by the number of values. So if you sum all these values, because the positive values and the negative values, they are similar, they are actually same, so when you sum them it will result into 0. So that means the mean value or the average value, or also called the DC value for this signal, it will be 0. Then you okay, then we take the next k equals to 1. So when k equals to 1, you understand I am expanding this equation, right? So it will be a1, right? And we say e power j omega naught t, and plus, then I write a2 e power j 2 omega naught into t, plus so on, right? So if you compare, right, so in the inspection method we expand this equation of synthesis and we compare the coefficients, right? So if you compare the coefficients, you can see this is e power j omega naught t, and we have e power j omega naught t. Then we have e power minus j omega naught t, so this is e power minus j omega naught t, right? So for all other terms this is 0, so we just take these two, and by comparing we can find that the coefficient of this one is a1, so that means a1 equals to 1 over 2j, or maybe I write a different color so that you understand. Okay, let me use this one. No, it's fine. Okay, so this is e power j omega naught t. So here e power j omega naught t, so that means this coefficient corresponds to this one, so that means a1 equals to, which I have written here, equals to 1 by 2j. Similarly, if you compare e power minus j omega naught t, so this is e power minus j omega naught t, so that means a of -1 will be basically equals to -1 over 2j, right? So this is what I mentioned here, and I say okay, ak equals 0 when k is not equal to, or you can also say when k is not equal to plus minus 1. So for all values, whether it's 0 or 2, 3, 4, -2, -4, and so on, for all values this is 0. So if you compare this with the analysis equation, which is this one, so that's quite straightforward, right? So for the sinusoidal signals or the complex exponential signal, we can straight away use the analysis equation, synthesis equation to find the Fourier series coefficients. So I hope this gives you idea how it works. Okay. So here's another example, and we have to find the Fourier series coefficients. So you understand these are basically the sinusoidal signals. So I think here, for sure, here the using the inspection method is lot easier, right? And it requires less work to complete to find the Fourier series coefficients, right? So this is your original signal where we have to find the Fourier series coefficients, right? So in this using the Euler identity or Euler formula, I can easily express these sinusoidal signals in terms of complex exponential signals, right? So I hope you understand, you know the relationship for sine theta, that's equal to e power j theta minus e power minus j theta divided by 2j, and for the cos it is for the cos theta, the Euler equation is e power j theta plus e power minus j theta divided by 2. Okay, so I use the same expression. So sine omega t, so that means e power j omega naught t minus e power minus j omega naught t divided by 2j. So I can write it also like multiply by 1 over 2j. Similarly, for the cos of omega naught t, I can write e power j omega naught t plus e power minus j omega naught t divided by 2. But because this is 2 times scale, so that 2 cancels with this one, so you get straight away this. Similarly, this one, so this is the phase with it, so we can say the theta is basically this whole, so we can write that for the this is cos, so I can write e power j 2 omega naught t plus pi by 4 plus e power minus j minus j and then times 2 omega naught t plus pi by 4, right? So then we collect the terms which have the same fundamental frequency, right? So we have a term 1 by 2j e power j omega naught t, and again we have e power j omega naught t. So if I write it together, right, or collect it, then I can write that this basically becomes 1 plus 1 over 2j e power j omega naught t plus, right? Similarly, for e power minus j omega naught t, we have here, and again we have here. So this has the coefficient 1 by 2j, and this is coefficient equal to 1. So that means 1 minus 1 over 2j e power j omega naught t. Again, I think similarly you can do for all of them, right? So in this way, you can easily find that using the synthesis equation, right? And the previous problem I have expanded that, so based on that you can say, okay, a naught equals to, right? So if you look at this one, so that means a naught equals to how much? 1, right? And then I say, okay, a, this is omega naught, so that means a1 equals to, right? So in the same way you can find of these, right? So to summarize, we can just write them like this, and because so these are your coefficients for this Fourier series problem, right? So you understand Fourier series coefficient, or in general we say Fourier is a complex operation, or the coefficients, they are complex. So complex means they have the real part and they have the imaginary part. So here they are mentioned as real and imaginary. So we can also write it in the form of magnitude and phase, right? So to express this in terms of magnitude and phase, so what will be its magnitude, right? So you understand magnitude is basically equal to real square plus imaginary square whole square root. So real is 1 square plus imaginary is 1 by 4, right? So 1 by 2 is basically squared, so 1 by 4 and the square root. So you get what? 5 by 4. What is the square root of 5 by 4? Okay, so that's what you get for this one. This is your A1. So A1 has magnitude equals to this one, right? So this is the magnitude for A1. Okay, similarly, what would be the magnitude of this DC term or the average value? So because it consists of real value only, and the real value is also positive, so that means it has a zero phase, and this same is taken as, so this is the coefficient A1 magnitude, and the phase of this will be 0, right? Similarly, what will be the phase of this one, right? So to find the phase, you say, okay, angle of AK, so this is A1, so I just write angle of A1, and this is equal to tan inverse, right? Imaginary over real, right? So if you do this, so you'll find that basically this is equal to minus 1 by 2, right? So minus 1 by 2 is the phase for this one, right? So again for this one, so you can do it for all these, right? So you can plot the magnitude response, which is this one, and you can also plot the phase response, which is this one. You understand magnitude response is the graph of the magnitude versus the frequency, right? And similarly, this is the phase response, is basically graph of the uh, phase versus the frequency, right? So in this way we can find the phase response and magnitude response for all these coefficients. Let's consider one more example. Here we have we have to find the Fourier series coefficient for this signal, and this signal is basically equal to e power minus t, right? So you understand it's an exponential signal which moves up very quickly and then drops slowly, right? Similarly, again at this point it reaches 0, it has the same value as it had at this point, and then similar fashion it moves up and then slowly decreases and reaches 0 at 4, and then again it reaches maximum and then starts. So this is continued, right? And also in this direction, right? So if you look at this one, this is periodic with period how much? 2. Okay, so if I integrate it, so to find the Fourier series coefficient, you understand in general we write this the equation for finding the Fourier series coefficients, that's 1 over t, and then integration over one period, and you write x of t times the e power minus j k omega naught t, right, and dt. Okay, so by replacing value, x of t equals to how much? E power minus 2t. So I write like this. So this can be, because both are multiplied, the bases are same, so power will be added, so this can be written as right, and the period is 2, so I just write 2 here, and I integrate it from 0 up to 2, and if you multiply you get something e power, you take minus j common, or maybe you like to take a j common, so it will be something like minus 2, right, and minus, oh, you cannot take j common because this term doesn't consist of j, so it's wrong. So let's take what common? Let's take the t common. Okay, so when you take the t common, you are left with minus 2 or maybe we take minus t common, so we are left with 2, right, and plus j k omega naught. Okay, so you're left with this one, and this your dt, and if you integrate it, so you get something 1 by 2, right, and when you integrate it, you get minus, right, this is 2 plus j k omega naught, right, and you get e power minus t, and then you have 2 plus j k omega naught, right, and the limits of integration are 0 to 2, so when you put 2 you get 2 minus 2, right, so that's minus 2 into 2, that will be minus 4, and plus, I think you can simplify it. So when you simplify it, you get the answer that is something like this. Okay, so that's quite straightforward, I think, right? So the next topic, I'll give you some of the numerical problems after the completing the Fourier series topic. So we come to the next topic, which is convergence of the Fourier series. Does the Fourier series converge for all the periodic signal, or there are some conditions, right, for the signals to converge, right? So these are called the Dirichlet conditions, and these are 3 conditions, right? So if a signal holds or satisfies all these 3 conditions, then we say that the signal that the Fourier series of the signal will converge. If it doesn't hold any or all of the conditions, then the Fourier series of that signal will not converge, right? So the first condition is that over any one period, x of t must be absolutely, right, these are for the continuous time. Similar arguments holds for the discrete time also, right? So we just over any one period, x of t must be absolutely integrable. That is, the integration of x of t over one period, the absolute value of this must be less than infinity. If this condition is satisfied, then we move to the next one, and for a signal to converge, it must satisfy all the 3 conditions. So one condition is this one. The second condition is, in any finite interval of time, x of t is of bounded variation. That means there are no more than finite number of maxima and minima during any single period of the signal. If this condition, right, so all of the conditions are important, must. The third condition is that in any finite interval of time, there are only finite number of discontinuities, right? So if a signal has finite number of discontinuities in the finite interval of time, then that signal has will converge, right, provided the previous 2 conditions are hold, right? So furthermore, each of these discontinuities is finite. Okay, so let's see different signals that are periodic but that do not hold these conditions, right? So the first signal that violates the first condition is x of t equals to 1 over t, right? Although this is a periodic, but if we right, so if you take this interval that is from 0 to t, right, so this is defined for one period, right? So this is if you look at this one, so it has the first condition, which is signal must be absolutely integrable, that is violated here. So this is the waveform of this signal. So this signal does not hold the first condition, so Fourier series will not converge for this signal, right? So we have an example of the function that meets condition 1, that is this signal is absolutely integrable. This is periodic signal with period equals to 0 to 1, right? So if I integrate it and take the absolute value of this, so it will give me some finite value. So that means first condition is hold, but the function has infinite number of maxima and minima in the interval. So you can see that it has, okay, so the Fourier series for this signal or this function will not converge. Here is another example of function that is a periodic and that holds the first two conditions, but the third condition is violated, right? So the third condition is there should be finite number of discontinuities, but if you look at this one, this has so many discontinuities, right? You understand what is a discontinuity? So discontinuity is an abrupt change where the one way to define it is that its integral, its derivative is infinite, right? So if something has this type of, so at 0 time, for example, it has value of 1 by 2, and at the same 0 time it has value of 1. Or if you talk about the drop, so it has value of 1 and it has a value of 1 by 2 without any change in time. So again, if you look at this one, so this is one discontinuity. Again, if you come here, so at this point it has value of 1 by 2, and again at the same time it has value of 1 by 4, that is, it is dropped to its half value, similar to what we had here, dropping to half value. Again, it's dropped to half value within no time. So if you see, so there are so many discontinuities involved in this one. Again, it goes to 1, right, within no time. So many discontinuities involved are here. So this means this is violating the third condition or the third Dirichlet condition. So this signal will not converge, right? So Fourier series of this signal will not converge. But the good thing is that the signals that do not satisfy Dirichlet conditions are generally do not typically arise in practical contexts. So all those signals that arise in practical contexts, they obey or hold all the three conditions of the Dirichlet, right? So that's a good thing, that the practical signal we come across, they generally hold all the three Dirichlet conditions. So before ending the lecture for today, let's take one example from the discrete time periodic signals, right? So for example, we have the discrete counterpart of the sinusoidal signal or the sine wave we have considered previously. Let we have x of n and x of n equals to sine omega naught n. Do you think this is a periodic signal? Right, so we cannot say whether it's a periodic signal or it's an aperiodic signal. For this signal to be periodic, 2 pi by omega naught must be an integer or the ratio of the integer. If this is the case, then we say the given signal x of n is periodic with period n. Now this is periodic with period n, so we'll use the same approach. We can also use the analysis equation, right? And we can also use the synthesis equation to find the Fourier series coefficients for this signal. So again, you can easily guess that if I expand it using the Euler identity, so it will be something 1 by 2j, and it will be e power, right, j omega naught n and minus e 1 by 2j and e to the power minus j omega naught n, right? So that's quite straightforward. Like if you recall the previous example for its continuous counterpart, so you can easily tell that basically these are the Fourier series coefficients, and this is basically A1, and this will be right, A of minus 1. So what will be the graph of this one? For the continuous time, if you recall, it was just two impulses, right? One impulse here, for example, that was, I don't exactly remember the values, but it's like this one, right? How much, by the way, it was, right? I think it was minus 1 over 2j, is it? And this one was, I think, 1 over plus 1 over 2j, right? And this was your frequency axis, and it was 0 for all. One thing, did you notice that these values of the coefficients, they exist on discrete values, right? I mean, they exist, for example, at 0, they exist at omega naught or minus omega naught. I'm talking about the general case, right? For example, if you recall the example of the square wave, right? So there you can observe that the graph made by these are the spectrum, we call it, right? The frequency domain graph, we call it spectrum. So spectrum for the square wave was discrete, if you recall. Can anyone guess why it's discrete, right? So again, I will not tell you why this is discrete, but you see these are zeros for all these values, okay? So how about the, so we had two impulses right here for the sine wave. Again, for this one, what will be the graph of this one? Do you think it will still be two impulses? Just think for a while. I give you some time, and then I'll show you the graph, and we will end with this. No, they will not be two impulses, right? Rather, they will be a periodic signal, right? So, for example, if you take its period to be 3, what is the period of this one? Is it 3, 4, 5? Okay, I'll leave it to you because I end the lecture here, and see you in the next lecture. We'll start the next lecture from this spectrum.